Welcome back to part 3 of lesson 19. So remember that what we're starting here is we're going to go back and fill in what the directions were. Okay, so the directions here are going to be dx1, and based on our calculations, what they were was 1 minus 2/3, 0 minus 1/3, 0 minus 2. Note how the three components we calculated in Jupyter go to the basic components. This is dx1. This is dx3. Oh. I am making little tiny typos. Okay. dx3 is 0 minus 4/3, 1 minus 2/3, 0, 6. And ds2 is equal to 0 minus 1/3, 0, 1/3, 1, 2. Again, note how the basic components were calculated using linear algebra and Python and NumPy in the other sheet, and we already knew what the non-basic components were. You'll see that the non-basic components, I'll circle those in red. Those are known, and it will be always the case that when you look at those non-basic components of the directions, they're going to be columns of the identity matrix, okay? Because they're going to be all zeros except 1, 1. So they're columns of the identity matrix, and that's by design. Okay, so now we need to calculate our reduced costs. C bar of x1. Remember, this is just the gradient transpose dx1. A little bit trickier here. It's going to be minus 2/3. Let's do it in the correct order here. It's going to be 8 times 1 plus and 9 times this minus 2/3, which equals 2. Right, 8 minus 6, so that's greater than 0. That's improving. C bar x3. Again, it's still this gradient test. Now it's 9 times the minus 4/3 plus 5, which equals 1 minus 1. Oh, I'm sorry, not minus 1. I clearly am not doing my adding. It's minus 12. It's minus 7. And then C bar S2 equals the gradient test again on ds2, which is equal to 9 times minus 1/3, which is just minus 3. Okay, so we are forced to use x1. That's the only improving direction. That's the only allowable direction we can use. And we have to do our step size calculation. Now we're going to have x2, which equals the x1 plus lambda times dx1, right? And we need that to be non-negative. So our x1, remember, there was 0, 0, 1, 0, 1, 0, 2. We're adding to that lambda times this direction, which is 1 minus 2/3, 0 minus 1/3, 0 minus 2. I'm only going to worry about the negative components here because those are the only ones that might go negative, might go infeasible. So that's 1 minus 2/3 lambda has to be greater or equal to 0. It'll be 1 minus 1/3 lambda greater or equal to 0. And 2 minus 2 lambda is greater or equal to 0. Notice that I only included the components of the direction which corresponded to negative directional components. Those were the x2, s1, and s3 components, all three of the basic variables, as it turns out. And what do I get? I get that in the first case, this says that lambda has to be less than or equal to 3/2. Oops. A lot of typos this time around. Sorry about that. Less than or equal to 3/2. Lambda has to be less than or equal to 3. And lambda has to be less than or equal to 1. So remember, this was the x1 component, this was the x3 component, and this was the s. Yeah, again, I'm making all these typos. These aren't x1 and x3. This was the x2 component, this was the s1 component, and this is the s3 component. So the winner here, the most restrictive, is the s3, and this becomes our leaving variable. So our new solution here, x2 equals, I'm going to add 1 for my step size. So it's going to be 1, 1/3, 0, 2/3, 0, 0. Okay. So that's using my step size of 1, and I see that my new basis, well, I have x1, x2, s1. My entering variable, which I knew from the get-go, was x1, and my leaving was s3. Okay. All right, so now I have to do a whole new set of calculations now. I just finished my second iteration, my second pivot, as we call it. And if you look at the Jupyter notebook, and I'm going to put a fourth video just to highlight one point about that notebook. There's one issue there. It'll only take a minute to describe, but I'll put it up as well. Anyway, if you look at that notebook and you see the directions that are calculated, well, what do we need for each non-basic variable? So we have a ds1, we have a dx3. Goodness, I keep making silly typos. dx3, ds2, and ds3. And what you'll find these directions to be are going to be 3 minus 10/3, 1 minus 5/3, 0, 0. The second direction you'll see is 1 minus 1, 0, 0, 1, 0. And the third and final non-basic directions are minus 1/2, 1/3, 0, 1/6, 0, 1. Okay. The reduced costs here, x3, again, it's the gradient transpose dx3. In this case, it's going to be 3 times 8 plus minus 10/3 times 9 plus 5. And what does that turn out to be? That's going to be, let's see, 24 minus 30 plus 5 is minus 1. C bar S2 equals, let's see, it's going to be 8 minus 9, which is equal to minus 1. And C bar S3 equals 8 times minus 1/2 plus 9 times 1/3, which equals minus 1. And guess what? There's no improving directions. We are done. Yay. Okay, so that concludes lesson 19, the simplex part. There's one more quick video, and it just goes into, again, one of these precision issues that we're going to see. But we would conclude now that the optimal solution here is this x2. This is an optimal solution. The optimal value, we just plug that into the objective. And if you do that, you're going to see it's 8 plus 3, it's 11. Okay. Note that we didn't know the optimal value at all until after we found the optimal solution. Anyway, this should be enough information for you to go ahead with the assessment. Do check out that 4th video, though, because there's a particular computational issue.